Let's start with thermodynamics beta. First one, work done by the gas. Work done by the gas. How do you calculate the work done beta? W is equals to integral of your P into your dV. Initial volume to your final volume. Okay. Or work done is also equal to area under PV curve. Area under your PV curve. Okay. So work done is being calculated with the formula W is equals to integral of your P into your dV, or work done is equals to area under your PV graph. Area under your PV graph part of relation. Okay. Let's see. Next one. For cyclic process, if I am taking the PV graph, okay, work done will be positive for clockwise and work done will be negative for anti-clockwise, whatever the area you're taking. For a cyclic process means if I'm starting from your A and if I'm coming like this. Okay, so this one is right now for me what? Clockwise. Work done will be your positive. If I'm taking right now here something like this. This is your PV graph and I'm coming in this one right now in the closed path. In the anti-clockwise direction. In the anti-clockwise direction, it will be your negative. Okay, clockwise direction, work done will be positive for cyclic process. For PV graph, this is for your cyclic process of your PV graph. Work done will be positive for clockwise, very important beta. And work done will be negative for your anti-clockwise. Clear? Same with third point. For VP graph, for your VP graph, if I'm going right now, V here on y-axis and pressure on your x-axis. For closed path, if I'm taking right now like this. Okay, so if I'm going in this direction, what is this one? Clockwise. So clockwise, it will be your negative. Work done in the clockwise will be your negative.
Positive, no, sir.
Yes, beta?
In the clockwise direction, the work done is positive.
For what?
Sorry, yes, sir, yes.
This is which graph?
Wave, volume and pressure, sir.
Volume and pressure. For the clockwise, work done will be your negative.
Okay, sir.
Sure. Next one. This one. This one is VP. And this one is also closed cyclic process. Right now, this one is in which direction? Anti-clockwise. So in anti-clockwise, it will be positive. So work done in your anti-clockwise direction will be your positive. Just opposite to your PV graph. Clear?
Yes, sir, clear, sir.
Sure. Take one example. Find work done for given graphs. For even given graphs. First one is, if I'm giving you the graph something like this. This is your pressure and this is your volume. Okay. Now I'm going from your A to your B, B to your C, C to your D, and D to your A. Work done from your A to B, B to C, C to D, and D to A will be equal to your how much? Okay, so that is your question. So we need to take area under the curve. I can directly take, if I'm giving you the parameters for this one. Here it is your P naught, and here it is your 2P naught, and here it is your V naught, and here it will be your 2 times of your V naught. Okay, so work done from your A to B, B to C, C to D, D to A will be equal to work done from your A to B plus work done from your B to C plus work done from your C to D plus work done from your D to A. Work done from A to B will be equal to how much beta? Area under this one beta? Pressure and volume. Area of this part. So this will be equal to V naught and this will be P naught. So it is your P naught into V naught plus work done from B to C. Volume is constant. So no change in the volume, 0. Work done from C to D. This total area beta. And graph under your D to C. This total area. This is will be equal to your volume is decreasing here beta. See. From C to D, volume is decreasing. So it will be your minus of your 2 times of your P naught into V naught plus D to A, volume constant. So work done will be 0. So this will be equal to your P naught V naught plus minus minus 2 times of P naught into V naught. That will be equal to minus of your P naught into V naught. Clear? Is that clear?
Yes.
Sure. One more example. Now tell me the answer for this one. This is your volume versus pressure graph. Volume versus your pressure graph. Okay. This one is your A, this one is B, this one is C, this one is D. This one like this one is like this one is like this one is like. This is in which direction, beta?
Clockwise direction, sir. We have to take negative.
P naught to P naught, and here it will be your V naught, and here it will be your 2 times of V naught. So obviously it will be what? Negative. Answer should be in the negative. So work done for me to go from A to B, B to C, C to D, and D to A will be equal to work done from your A to B plus work done from your B to C plus work done from your C to D plus work done from your D to A. Work done from your A to B will be equal to how much beta? Pressure P naught into V naught, area under this curve. Okay, plus work done from B to C, volume constant 0. C to D, this total area. So here to here it is your 2P naught. So it is from your C to D, volume is decreasing, you see. If you're coming from C to D, volume is decreasing. So it is minus of your 2P naught to P naught into your V naught plus work done from D to E, again volume constant 0. So we are getting this one as P naught V naught minus 2 P naught into V naught. So answer will be obviously negative of your minus of your P naught into V naught. Is that clear for everyone? Is it clear? Chalo. Work done by any processes beta, it always depends upon the given conditions. I hope you are clear with this one, everyone. Chalo, next one. Zeroth law of thermodynamics. Zeroth law of your thermodynamics. What do you mean by that one, beta? Like say, if this is system A and this one is your system B. If A, temperature of your A is equals to temperature of the B, that means can I say that A is in thermal equilibrium with your B? In the same way, if I take the system B and if I take here the system C, okay, going from C and this one. So temperature from your B must be equal to temperature of your C. See, if A, temperature of A and temperature of B are same, then A and B are in thermal equilibrium with respect to each other. If the temperature of the B is equal to temperature of the C, that means B is in thermal equilibrium with your C. Then I can say that, what I can say, beta? A is also in thermal equilibrium with your C. A is also in thermal equilibrium with your C, because temperature of your A will be equal to temperature of the C. Is that clear? If A and B are in thermal equilibrium and B and C are in thermal equilibrium, then A and C are also in the thermal equilibrium with respect to each other. We'll get only the theoretical question based upon that beta. What do you mean by zeroth law of thermodynamics? If the system A and B are in thermal equilibrium and B and C are in thermal equilibrium with respect to each other, then A and C are also in the thermal equilibrium with respect to each other. Is that clear? Sure. Next one. First law of thermodynamics. First law of thermodynamics. First law of your thermodynamics. Okay. So also called as of your float. FLOT, float. So what is the first law of your thermodynamics, beta? D cube will be equal to your du plus of your dw. D cube is equals to your du plus of your dw, and it is based on law of conservation of energy. Okay. Du is known as internal energy. Du is known as of your internal energy. That will be equal to your F by 2 N into R into your temperature. That is nothing but of your dt. Okay. dW is your work done. dW is equals to your work done. That will be equal to pressure into change in volume. So therefore I can write d cube is equals to F by 2 N into R into your dt plus work done will be equal to your integral of your P into your dV. So I can write like this. Here also integral of your P into dV. Okay. So if I'm taking the sign conventions for this one. If I'm taking your sign convention, number 1, dq. dq is positive if heat is given. dq is negative if heat is taken. Okay. Next one, du. du depends only on temperature, beta. Internal energy depends only on temperature. So du will be equal to positive if temperature increases. du will be negative if temperature decreases. Okay. Then dw. dw work done will be positive if volume increases. Work done will be negative if volume decreases. Clear, beta? That is a basic sign convention of this. dq will be positive if heat is given. dq will be negative if heat is taken. And it depends, internal energy depends only on temperature. But if the temperature is increasing, it will be positive internal energy, or else it will be negative. Why? Because internal energy is equal to how much for me? F by 2 into N into R into your dt. So F is a constant, 2 is a constant, N is a constant, R is a constant. So it depends only on your temperature difference. Clear for everyone? Any doubt in this one? Sure. Next one. Work done in different thermodynamic processes. Work done in your different thermodynamic processes. Okay, first one. Isochoric process. Isochoric process. In isochoric process, what remains constant, beta? Volume. volume is constant. So when volume is becoming for me constant, I can write here work done will be equal to how much for me beta? dW will become for me 0. Work done will be equal to 0 because differentiation of your any constant will be 0. Okay, I'm not writing that one. Applying first law of thermodynamics. dq is equals to du plus of your dw. So dq will be equal to your du. dq will be equal to your du. Therefore, dq will be equal to your f by 2 into n into r into your dt. So dq is equals to your f by 2 nr into your dt. F is your degrees of freedom beta. F is your degrees of freedom. Degrees of freedom. So F is equals to 3 for monoatomic. F is equals to 5 for diatomic. Okay. F is equals to 6 for your triatomic. Linear I'm taking right now. Okay. Therefore, dq is equals to 3 by 2 nr into your dt for monoatomic. And dq will be equal to your 5 by 2 nr into your dt for your diatomic. Like that I can write the relations. Okay. So dq will be equal to f by 2 nr into your dt for your isochoric process. In isochoric process, volume remains constant. So work done will be equal to 0. Applying the first law of thermodynamics, we are getting dq is equals to du. That means dq is equals to f by 2 nr into your dt, where n is your degrees of your freedom. F is equals to 3 for monoatomic, F is equals to 5 for your diatomic, F is equals to 6 for your triatomic. Therefore, I can write dq is equals to 3 by 2 nr into dt for monoatomic and dq is equals to 5 by 2 nr into dt for your diatomic. Clear, beta? Graphs. See, first one. If I am drawing your pressure versus volume graph, beta. Pressure versus your volume graph, PV graph. So if I take your P and V graph right now, volume is remaining constant, so it will be a straight line like this. Okay, next one. So if I'm taking the next graph right now for this one, P versus your temperature graph, pressure versus temperature. Okay, use PV is equals to nRT beta. Okay, so we need to draw the graph between P and T. So P will be equal to N into R into your T divided by V. So P is equals to, this total is right now for me a constant because N is a constant, R is a constant, volume is also constant. So it is KT. So compare it with Y is equals to M into your X. On y-axis pressure, on x-axis temperature, so we'll get a straight line passing from the origin, making an angle theta. So your K value is equals to how much beta? K value is equals to N into R divided by your V. K is nothing but equal to your slope Em, isn't it? That means N into R divided by V will be equal to tan theta. Or else I can write theta is equals to your tan inverse of your N into R divided by V. That will be the volume. So theta will be equal to your tan inverse of your N into R divided by volume. So I can say that tan theta is inversely proportional to the volume. More the angle, lesser will be the pressure. Like say if I give you a small example, if there is a graph between pressure versus your temperature and three different graphs are given like this. These are say volume V3, this one is V2 and this one is V1. And this one is making an angle theta 1, this one is making an angle theta 2 and this one is making an angle theta 3. So obviously tell me which angle is more beta here right now. Theta 1 is greater than, theta 2 is greater than theta 3. Okay, so obviously V1 will be lesser than V2 will be lesser than V3, or else I can say that V3 is greater than V2 is greater than V1. Clear, beta? Is that clear? Is that clear? Graphs. Sure. Next type of a graph I'm going, beta. Isobaric. Work done in an isobaric. Isobaric, what remains same, beta? Can anyone tell me? Baric means pressure. Pressure P is equals to your constant. If the pressure P is equals to constant, okay, from first law of thermodynamics, dq will be equal to your du plus of your dw. That means dq will be equal to your f by 2 n into r into your dt plus work done will be equal to pressure into change in volume. Or else I can write dq is equals to your f by 2 n r into your dt. From ideal gas equation, P into delta V will be equal to nr into your dt. So dq will be equal to your f by 2 plus 1 into nr into dt will be your constant. So dq is equals to your f by 2 plus 1 nr into your dt. Clear, beta? dq is equals to f by 2 plus 1 into nr into your dt. That will be your isobaric pressure. Okay. Any doubt in this one to anyone? Tell me the graphs for this one. First one is pressure versus volume graph. PV graph. What is the remaining constant? Pressure. So it will be a straight line like this, parallel to x-axis. If I am taking next graph is volume versus your temperature graph, VT graph. So it will be a straight line passing from the origin, theta, Charles law. Okay, I'm using the relation PV is equals to NR into your T. So P will be equal to NR divided by V into T. So I need a graph between V and T now. So I'll take here V right now. So V is equals to NR divided by P into T. This is total constant. So V is equals to some constant K into T. Comparing with your Y is equals to your M into your X. So what I'll be getting right now from this one? M is nothing but equal to your K. That means tan theta will be equal to K. K is your NR divided by P. That means tan theta is inversely proportional to your pressure. Clear? Take an example for this one, beta. Like say, this one is VT graph. No? So this is your volume and this is your temperature. So if I take the graphs like this one. This one is at your pressure P1, this one is P2, this one is P3. This one is your theta 1, this one is your theta 2, and this one is your theta 3. So obviously theta 1 is greater than theta 2 is greater than theta 3. So what I told you, tan theta is inversely proportional to pressure. So if theta 1 is greater, so P1 will be lesser than P2, P2 will be lesser than P3. Or else I can say that P3 is greater than P2, P2 is greater than of your P1. Any doubt, anyone? Is it clear? Clear, beta? Sure. See it once again. Work done in different thermodynamic processes. For isochoric process, work done will be 0. Applying the ideal gas equation, dq is equals to du. So dq is equals to your f by 2 nr into your dt. Done, beta. So dq will be equal to f by 2 nr into dt. F is known as of your degrees of freedom. F is known as of your degrees of your freedom. For monatomic gas, it is your 3. For diatomic gas, it is 5. And for triatomic, it is your 6. Next one is graphs. Just now I told you, you can just go through it. Isochoric process, pressure remains constant from first law of thermodynamics, dq is equals to du. So we are getting dq is equals to f by 2 plus 1 into nr into dt. Pressure versus volume graph, if I'm drawing, we are getting a graph which is parallel to your x-axis. And Vt graph, it will be a straight line passing from origin. Tan theta will be equal to your how much for me? nr by your p. Or else theta will be equal to your, I can write tan inverse of your n into your r divided by your p. Clear, beta? Sure. Just a minute, beta. Sure. Let us try to do some problems based on this one, beta. First question. In changing the state of thermodynamics from A to B, the heat required is Q and the work done by the system is W. The change in the internal energy will be equal to how much, beta? Can anyone do it, beta? Anyone? Option A. See it carefully. Isn't it? Delta Q is equals to delta U plus delta W, beta. So internal energy means delta U is equals to delta Q minus of your delta W. So using the proper signs, I can write Q minus of your W. So which will be the answer for this one? B will be the answer. Next one. The temperature of an ideal gas is kept constant as it expands. The gas does external work. During this process, the internal energy of the gas increases, decreases, remains constant, depends on molecular motion. Internal energy depends upon the temperature of the gas, beta. Temperature of an ideal gas is kept constant as it expands. So the gas does the external work. During this process, the internal energy of the gas will remain constant because Internal energy depends only on, I told you, internal energy depends on temperature, not any another condition. So if temperature remains constant, internal energy will also remain constant. Next one. A thermodynamical system is being changed from state P1 to P1V1 to P2V2 by two different processes. The quantity which will remain same will be equal to your how much? Can anyone tell me better? See, if I'm writing the change in internal energy does not depend upon what beta path. It is independent of your path because it depends upon only the temperature. So if I write internal energy, that will be equal to your delta Q minus of your delta W, which remains for me constant. Okay, change in internal energy will depends on temperature. And I can say that does not depend upon path, whether it is clockwise or anti-clockwise, it is independent. So dq minus of dw will be remaining constant, internal energy, because dq will change, dw will change. Dq plus dw is nothing but what for me? It is not possible. So delta u is equals to delta q minus delta w. Clear, beta? Sure. Next one. For the free expansion of the gas, which of the following is your true? For free expansion, which of the following is true? Q will be equal to W is equal to 0 and the change in internal energy is equals to 0. Q is 0, work done will be greater than 0. Work done by the change in internal energy is negative of work done. No, it is not possible. Internal energy will become 0, whether it will be in the first option or fourth option. If Q is equals to W is equals to 0, okay, that will be possible because delta Q is equals to delta U plus delta W. Okay, so if delta Q is 0, delta U plus this one is also 0. So delta U is also your 0. So A option will be the answer. Sure, next one. The specific heat, I have not done still this one, we'll do it later. And then 1 mole of your internal energy. Can anyone tell me this one right now, beta? 1 mole of an ideal monatomic gas is heated at a constant pressure of 1 atmosphere from 0 degrees centigrade to 100 degrees centigrade. Then change in internal energy will be equal to how much? So change in internal energy always supplies the heat, beta. So it is your delta Q at your constant volume. That will be equal to your N into CV into your DT. For monoatomic gas, I told you in expansion of kinetic theory of gases, for monoatomic gas, CV will be equal to your 3 by 2 into your R. So internal energy will be equal to your N into, this one is your 3 by 2 into your R into temperature difference. That is nothing but delta T. That means that will be equal to your how many number of moles? 1 into your 3 by 2. R value is 8.3 into temperature difference is 0 to 100. That means 100 part of relation. So simplify it, you will be getting the answer for this one. See how much I am getting? Anyone? Du is equals to your N into 3 by 2 into R into delta T. Everything is given. So it is 1 into 3 by 2 into your 8.5. Option C, 12 point, yeah. So it will be your 12.48 into 10 to the power of 2 joules. Next one. In the thermodynamic process, next one, try join and everyone. In a thermodynamic process, the pressure of the fixed mass of the gas is changed in such a manner that gas releases 20 joules of heat and 8 joules of work is done on the gas. If the initial internal energy of the gas was your 30 joules, the final internal energy will be equal to your how much? So given in the problem, thermodynamics process, pressure of the fixed mass of gas is changed in such a manner that gas releases 20 joules of your energy. It releases means delta Q is equals to minus of 20 joules. And 8 joules of work is done on the gas. If work is done on the gas means work done will be equal to minus of 8 joules. Okay. And initial internal energy was 30 joules. That means initial internal energy is equals to your 30 joules. final internal energy will be equal to your how much? We know the formula, delta Q is equals to your delta U plus of your delta W. So delta U will be equal to delta Q minus of your delta W. So it is your U final minus of your U initial is equals to, I can write here right now for me, delta Q will be equal to how much for me? Minus 20 minus of your 8. U initial, we need to calculate it. U initial is given how much for me in the problem? 30. That is equals to minus 20 minus this will be equal to your plus 8. So that will be equal to how much for me? U final will be equal to how much? 80. 18 joules. Clear? U final is equals to your 18 joules. Done? Sure. Next one. If delta Q and delta W represents the heat supplied to the system and work done on the system respectively, then the first law of the thermodynamics can be written as of your how much? So from the first law of thermodynamics, I know the formula dQ is equals to your du plus of your dW. So du will be equal to how much for me beta? dQ minus of your dW, isn't it? So here right now du will be equal to your dQ, which will be lesser than of your 0 beta, isn't it? Because work done will be equal to how much? Because work done will be equal to 0. Delta Q and delta W represent heat supplied to the system and work done on the system respectively. Then the first law of thermodynamics can be written as of right now. Delta Q is equals to delta U. That means I can write delta Q will be equal to delta U plus delta W. Directly first one I can write it out now. Because internal energy will be lesser than 0. So temperature will be decreasing. Isn't it? So I can directly write, otherwise there is not much required. Is all there is a data. dQ is equals to your du plus of your dW. Let me see the question right now once again. See the question better. Am I wrong in this one? Yeah. 8th one. Sir, how to remember all the formulas of physics? I face problems in remembering the formulas. You need to practice it better. There is no other alternate. See, when you're reading some chapter and you're doing some chapter, you should know what is important, what is not important. At least on standard relations, you need to write it them twice and thrice without seeing. Otherwise, it is not possible to do the problems. Sure. If delta Q and delta W represents the heat supplied to the system and work done on the system. Work done on the system means it will be your negative. It will be your negative, isn't it? That means right now I can write from this one, first law of thermodynamics, delta Q will be equal to delta U minus of your delta W. That means second option will be, sorry. Next one. In the given process for an ideal gas, dW is 0 and dQ is lesser than 0. Then for the gas, the temperature will decrease, the volume will increase, the pressure will remain constant, the temperature will decrease. So use the first law of thermodynamics beta. dQ is equals to your du plus of your dW. Internal energy will be equal to how much beta? dQ minus of your dW, isn't it? So that means I can write here du will be lesser than of your 0 because work done will be equal to how much for me? 0. dW is equals to your 0 right now if I'm taking. So du will be equal to dQ and dQ is lesser than of your 0. If du is lesser than 0, so temperature will, so it is nothing but of your F by 2 nR into your N into R into your dt will be lesser than 0. So the temperature will be decreasing. The temperature will decrease. A will be the answer. Then, madam. Next one. Out of the following, which quantity does not depend on path? Temperature, energy, work, none of them. Can anyone tell me better? Temperature depends only on initial and final. It is a path independent, like internal energy. Direct question. Next one. A thermodynamic system undergoes a cyclic process A, B, C, D, A as shown in figure. The work done by this process will be equal to your how much? Can anyone do this one better? See a direct question right now. Cyclic process, work done from your B, from this relation if I'm writing, B to C, C to your O and O to your B will be equal to how much for this one? Volume is decreasing better. From B to C, volume is decreasing. So obviously your answer will be in the negative. So it is negative of area of your triangle BCO. So that will be equal to minus half of your P naught into V naught. The same way, work done from your A to O to D, D to A will be equal to positive area of triangle AOD. So that will be equal to plus of your half into P naught into your V naught. So work done will be equal to how much work done? Work done during cyclic process will be equal to 0. So this will be the answer. Clear, beta? So next one. The system is taken through a cyclic process represented by a circle as shown. The heat observed by the system will be equal to, see in the cyclic process, if I'm writing delta Q is nothing but what beta for me? Work done. That is nothing but area inside circle. In cyclic process, internal energy will be equal to 0 beta. From first law of thermodynamics, if I'm writing dQ will be equal to your du plus of your dw. So internal energy will become 0. That is the reason dQ will be equal to your dw. dQ will be equal to dw. dw is nothing but work done is nothing but area inside your circle. So if I'm writing the area inside the circle right now, so work done will be equal to, that is nothing but dQ. dQ will be equal to your area of this one. Area of what right now? Area of, treat the circle as of an ellipse beta. So it will be your area of your ellipse. Why ellipse means this side and this side and this side and this side are not same. This is your 50 and this one is of your 50. This one is 100 and here it is nothing but of your 10 and here it is nothing but your 10, 20. So it is not forming a circle right now. Even though it is appearing to be circle, it is not a circle if you see it very carefully. That means it will be equal to area of an ellipse. Area of an ellipse means dQ will be equal to your, this will be equal to pi by 4 into your P2 minus of your P1 into V2 minus of V1. So that will be equal to your pi by 4 into your, this is your P2 150 minus of your 50 into, this will be equal to how much for me beta? V2 minus of your V1. V2 is 40, 40 minus of your this one. How much it is beta? It is your 40, 10, 40 minus of your 20. That will be equal to 20 in cc. So it is a 20 into 10 to the power of your 3 cubic centimeter. Clear? Okay, kilopascal now, cubic centimeter 10 to the power of minus 6. This one is 10 to the power of 3. So simplify, we will be getting 150 pi by 4, 150 minus 50 into 20 into 10 to the power of 3. See how much I am getting better. So it is pi by 4 into 150 minus 100 into 20 into 10 to the power of 3. Okay. So if I simplify this one, this will be 2 tens are 2 twos are. So that will be equal to your pi by 2 into, the remaining part will be equal to how much beta for me? Pi by 2, how much I'm getting, you say? I'm doing calculation correctly only, you say this one is 10 to the power of 3 and this one is 20 cc. 1 cubic centimeter will be equal to, that means 1 cubic centimeter. This is 1 cubic centimeter. That means centimeter cube. 1 centimeter cube. That is 10 to the power of minus 2 whole cube. That means this is 10 to the power of minus 6. So into 10 to the power of minus 6 I need to do. So it is your 10 to the power of 3 into 10 to the power of minus 6 into this one is 10 to the power of 3. So every one will get cancelled, pi by 2 joules. So it will be B will be the answer for this. Next one. Change in internal energy. Can anyone give me the answers process better? In the diagram shown from 1 to 4 of variation of volume with changing the pressure is shown, a gas is taken along the path of A, B, C, D. The change in internal energy of the gas. See, for internal energy for any cyclic process will always be 0 beta. So it will be 0 for all the cases. Direct question. Because internal energy will depend upon your what? Change in temperature difference. Initial and final temperature is 0. So internal energy will be 0 for all the cyclic processes. Direct question. The next one. In thermodynamic process, 200 joules of heat is given to the gas and 100 joules of work is done on it. The change in the internal energy of the gas will be equal to your how much? Now see here right now, 14th one, delta Q will be equal to your delta U plus of your delta W. Delta Q is given how much for me? 200 joules. And work done is equals to work done on the gas, it is minus of your 100 joules. So internal energy will be equal to delta Q minus of delta W. That will be 200 minus of your 100. That will be equal to your 300 joules. Direct question. Done. Next one. 110 joule of the heat is being added to a gaseous system whose internal energy will be 40 joules. Then the amount of this one whose internal energy is 40 joules. Then the amount of the heat. So heat is being given. Then the amount of work done. 110 joule of your heat is being given for me. That means delta given amount of work done. I'll write here. So tell me what will be the answer, beta? Delta Q is equals to delta U plus of your delta W. So delta W will be equal to delta Q minus of your delta U. Delta Q is 100 minus this one is 40. That will be equal to 70 joules. A direct question. Next one. An ideal gas of mass M in a state A goes to another state B. Okay. Via three different processes as shown in the figure. Q1, Q2, Q3 denotes the heat absorbed by the gas along the three paths. Then which one, what will be the relation in this one? Can anyone tell me the answer for this one, beta? Area under the PV graph will give me what? Heat absorbed. See, initial and final states are same in all the process, beta. So I can say that delta U will be equal to 0. From the first law of thermodynamics, I can say delta Q will be equal to delta W. That is nothing but of your area of your PV graph. So now just see the areas of this one. Area of 1 is lesser than of your area of your 2. And area of 2 is lesser than of your area of your 1. That means Q1 will be lesser than Q2. Q2 will be lesser than of your Q3. So in this one, this will be heat absorbed. Okay. Next one. The monatomic gas of N moles is being heated from temperature T1 to T2 under two different conditions. Number one, at constant volume. Number two, at constant pressure. The change in internal energy will be equal to how much? Internal energy formula I told you, delta U is equals to N into your CV into your DT. So it doesn't depend upon the type of process, beta, because it is a state function. So it is at a constant volume if I'm taking right now, beta, for number one. And two different conditions at constant volume and constant pressure. The change of internal energy of the gas is more in your two part. Clear, beta? Chalo. Try to do this one, beta. 18th one. A perfect gas goes from the state A to the another state B by observing 8 into 10 to the power of 5 joules of heat and doing 6.5 into 10 to the power of 5 joule of external work. If it is not transferred between the two states and another process in which observes 10 to the power of 5 joule of heat, then in the second process, the work done by the gas is how much? Sure. So in this one, first law of thermodynamics, delta Q is equals to delta U plus of your delta W. Delta Q is given as 8 into 10 to the power of 5. That is equals to delta U plus this one is your how much for me? 6.5 into 10 to the power of 5. So from this one, you find out the internal energy. Internal energy will be same for both the process, beta, because it is independent of the path. It only depends upon the temperature difference. Just calculate it, whatever the answer you'll get, that will be the answer for that. How much you're getting, you see? Just I'm leaving the calculation for this one for you. Please try to do that one. Next one, when heat energy of 1500 joule is being supplied to a gas at a constant pressure 2.1 into 10 to the power of 5, there was an increase in its volume equal to 2.5 into 10 to the power of minus 3. The increase in internal energy will be equal to how much? Direct question, beta. Delta Q will be equal to delta U plus of your work done. So that will be equal to delta U plus of your P into your delta V. This is your delta Q. So internal energy will be equal to how much for me? Delta Q minus of your pressure into your change in volume. So delta Q is given how much for me? 1500 joules minus this one is 2.1 into 10 to the power of 5 into this one is 2.5 into 10 to the power of minus 3. To simplify it, we'll get the answer for this. I'm leaving the calculation for you. Just try to do the calculation on your own. Next one. If a system undergoes the contraction of volume, that means volume is decreasing, then work done by the system will be equal to how much? Work done will be equal to P into delta V. Here delta V will become for me negative. So work done will also become for me negative. Okay. Sure. I have already sent you some of the assignments better on thermodynamics 1. You please try to start doing them. Okay, on app also we have been uploaded the assignments. You please try to go through them once. Okay, sure. Take care, beta. Bye.